We discuss Kirchhoff's rule in this lecture. In the last lecture, we have learned that we can use the method of equivalent resistor to solve a class of direct current circuit effectively. However, there are ways in which the resistors are connected, that we cannot reduce it to a single equivalent resistor. Generally speaking, if there are more than one battery or EMF in the circuit, then it cannot be reduced to a single equivalent resistor. In such a case, we need to use Kirchhoff's rules. There are two statements of Kirchhoff's rules. The junction rule states that at a given junction, the current goes in the junction has to equal to the current goes out from the junction, which is really a statement of conservation of charge. You can also translate that into the charge goes into a junction equals to the charge goes out of the junction for any amount of time interval. So that's junction rule. We also have loop rule. The sum of potential difference across all the elements around any closed circuit loop must be zero. This statement is a statement of conservation of energy. We can compare the junction rule to water flow. So we can have a larger pipe which is split into two smaller pipes. We have a larger water flow in that larger pipe. So the water in those two branches of a water pipe has to sum up to the water flow in that main pipe. This also applies to electric current. If I have current goes into this junction, let me call it I1. And at this junction, it is split into I2 and I3 because of charge conservation. The current goes out from the junction, which is I2 plus I3 has to add up to I1. In order to apply Kirchhoff's rule, we need to assign simple and direction to the currents in all branches of the circuit. And don't worry if you choose the direction wrong. We'll just go ahead and solve it. If the assigned direction is wrong, we will solve a negative current in the direction we assigned, which means in reality the current goes in the other direction of our choice, but we still solve that problem. When applying the loop rule, remember that we have to choose a direction for the loop, either clockwise or counterclockwise. There are certain rules for loop rule. Let's choose the direction of the loop goes from A to B. Now, if the current also goes from A to B, then point A is higher potential compared to point B. So when we travel from point A to point B, we would have a drop in potential. And that drop of potential will give us a minus IR potential drop when we travel from A to B. This is for current in the same direction as the loop. On the other hand, let's keep the loop direction still goes from A to B, but the current is going from B to A. In this case, VB is a higher potential compared to VA. But we are traveling from A to B. So when we travel from A to B, we'll have an increase of potential equals to plus I times R. So when the current is in the opposite direction of the loop, for the resistor, we would have a potential increase of plus IR. Now let's discuss loop rule for battery. We still keep the loop goes from A to B. Now if from A to B we travel from negative terminal of battery to positive terminal of the battery, then we would have a potential increase, which is equal to the potential of the battery, which is intuitive because B would be higher potential compared to A. So when we travel from A to B, we're going to have potential increase. On the other hand, if A is connected to the positive end of the battery, B is connected to the negative end of the battery, we travel from A to B, we would have a potential drop equal to minus epsilon. Now, let's have an example. In this example, we have two junctions, point A and point B, but you can check point A and point B will give us the same junction equation, the same equation for the currents. Now we have the current that goes into junction A is I1. The current that goes out from A is I2 plus I3. So the junction rule gives us I1 equals I2 plus I3. You can check by yourself that if you do the same for junction B, you'll get the same equation, I1 equals I2 plus I3. Okay, now we can have three loops. We can have loop 1. I have choose loop 1 to be clockwise. Actually, I choose all loops to be clockwise. Loop 1, loop 2, loop 3. Let's start with A for all the loops. For loop 1, we start with A. The loop direction goes from A to B. Current I2 is in the same direction as loop direction. So I'm going to have a potential drop, which will give me minus I2R2 for R2. I move from A to the left. I will have epsilon 1. And follow the loop, I move from right to the left. So I'm moving from negative end of epsilon 1 to positive end of epsilon 1 till I reach B. So I will have a potential increase, which is plus epsilon 1. Now I'm at location B. Following loop 1, I'm going to point C. Nothing happened. I then go from point C to point D. The loop direction goes from C to D. The current going through R1 is I1. I1 is pointing in the same direction as loop. So I'm going to have a potential drop for R1 as well, which gives minus I1 R1. So now from D, I go back to A, which complete my loop 1. So I have an equation for loop 1. I do the same thing. From A for loop 2, from A to E, nothing happens. From E to F, I have a potential drop for R3, which is minus I3 R3. I have a potential drop for epsilon 2, which gives me minus epsilon 2. And after epsilon 2, I arrive at F. From F to B, nothing happened. I still need to follow loop 2 from B to A. From B to A, I have a potential drop for epsilon 1. And then I have a potential increase for R2, which is plus I2 R2. And then I goes back to A. So I complete my loop, which gives me the second loop equation. I can do the same thing for the big loop, loop 3. I still start with A. A to E, nothing happened. E to F. I have a potential drop for R3, which is minus I3 R3. I have a potential drop for epsilon 2, which is minus epsilon 2. Then I'm at F. From F, I goes to B, nothing happened. For the loop 3, I goes to C, nothing happened. From C to D, I have a potential drop for R1, which is I1, R1. Now from D to A, I complete my loop. So I got my loop 3 equation. So now it depends on what quantity are given by the problem. We put in the values given by the problem and solve those equations for unknowns. Unfortunately, for Kirchhoff's rule, usually we need to solve a linear set of equations, a set of linear equations.